Okay, so we are going to continue our discussion today of collisions, and in order to do that, we want to review our two types of collision. So let's find that slide, and I want to talk about the difference between collisions. So we have elastic collisions, which we saw, in which momentum is conserved and energy is conserved, and completely inelastic collisions, in which momentum is conserved but energy is not conserved. And we saw that inelastic collisions, non-completely inelastic collisions, sort of represent this intermediate step. And we'll find that while most real-life collisions some energy lost, making virtually every collision some sort of inelastic collision, that's not helpful in sort of classifying these things. Because if you only lose a tiny bit of energy, you can look at the properties and say, I have an elastic collision. And then you will see stuff where it's completely inelastic, which is the objects stick together, and there's a maximal loss of kinetic energy. All right? So when we solve problems, we're going to stick to elastic collisions and completely inelastic collisions. And if you recall, we had criteria for elastic collisions, and we did this problem with the bullet where it was a completely inelastic collision in one part, and then energy was conserved after the collision. We had an energy conservation problem here and a momentum conservation problem here. And I want to remind you the difference between that, between what we're doing in this problem and in an elastic collision. In an elastic collision, in one event, both energy and momentum would be conserved. That's not happening here. We have two events, two problems. One problem is a completely inelastic collision, and then we have a second problem that is an energy conservation problem. And we match those two problems together at the boundary. All right, and the boundary being when this stops moving, it has some velocity, and that initial velocity, or that final velocity of the collision, becomes the initial velocity of the second problem. All right, if you want to see that in detail, look at last week's video. It's all there in gross detail. Now we saw for elastic collisions, right? The equations could be very easy if we had a object hitting a target, right? A non-moving target. Everything looks pretty good. It's when the two objects are moving that we can have potentially this very long, it's again, this is the point where the algebra is the hardest part of this, right? Once you have the equation, you're fine. And we did a checkpoint. So now what we want to do is we'll recall that we've been sticking to one dimension, but momentum is a vector. So we are able to apply our momentum conservation in 2 dimensions, all right? And we'll note that momentum is conserved in the x direction and in the y direction. We saw that when we talked about impulses, right? If you remember that problem where we had the car hitting up here like so, and it just changed direction in the x-axis, not in the y-axis. It was something like that. We either did an example or a checkpoint like that. So when you have a problem like this, you have 2 steps. All right. So the first step, given by this bullet point here, is apply conservation of momentum along each axis. So that means you want to figure out Px initial will equal Px final, and Py initial will equal Py final. Some things to recall here is that the momentum is equal to mv, right? So you know what you're breaking up into and looking at. Now, then you have to identify if the collision is elastic or inelastic, all right? And if it's elastic, you have this extra step of applying the conservation of energy, all right? And there it's just E initial equals E final, because remember, energy is a scalar, so the direction doesn't matter, all right? So this can give you a total of, let's see, each component gives you one equation, so you can solve for a total of 3 unknowns, which can be a little jarring, right? If you have an elastic collision and they don't give you 3 things, you can solve for up to 3 quantities. Okay? So now let's look at a simple example here where we have an object, mass 1. You'll notice we have our initial, so mass 2 is stationary. I'm going to circle this in blue. We have our initial situation, and then we have our final situation. I need to not include that other mass. There we go. There we go. All right, so you notice we have our initial and final situation, okay? And you'll just have to pretend with me that this mass 1 is in the circle here. But I want you to notice that when you're doing a momentum problem, this is exactly what I mean about, I'm not going to ask you a chapter 3 problem, but you definitely have to have chapter 3 down to do these problems, because momentum is a vector, right? We want to add our arrows. And so when we're doing this, we're going to have to regularly break our momentum into the correct components every time we do it, okay? And so when we look here, we notice on the initial side, we look in the x direction. So let's look at each particular part. We notice M1, V1 is moving along the x direction. So you write that down here, okay? And that equal, and then we go to M2 in the initial. And M2 you'll notice is stationary. So this is going to be M1, V1 plus 0. So that's why there's no second term here. And that gives us the initial side. Are there any questions on the initial side? So I'm just looking at the x direction only now. So if you have a question, if you're asking what about y, I'm not there yet, so I can't answer. I will soon, but we're not quite there. And I'm only talking about this side of the equation. All right? So I'm only looking at these 2 particles. Are there any questions about writing that part? Or we to Spring 2, I don't have anyone to teach the 232, unfortunately. So no teachers means no class. For Daniel asked about a 232 section. Yeah, that's one of those that's one of those fundamental things. I know there's student interest in it, but yeah, I'm not willing to have it's hard to do in the summer, and my superiors do agree that a full-timer should teach it, and I don't have an available full-timer. So, all right. So any questions, though, on this side of the equation? The left-hand side. Pretty straightforward. I'm hoping it should be pretty simple. But all I've done, if there is anything, is I'm just recognizing. I'll expand it, right? So when I look at it, I'll write it in yellow up here. So for the left-hand side of x, left-hand side of x, px is pi. All right, and that's that first equation that says along x. And basically, I've seen that px initial is equal to p1 initial plus p2 initial. And without looking at anything, I can use my definition of momentum to plug everything in, right? If I look at the picture, I see right here that m1 is moving with velocity v1, right? So that's velocity, not speed. You've got to be careful. And then so that's going to equal the pen has failed me. M1, V1, right? Initial. And then I can look at the other, at P2. If I look right here, this mass is stationary. So that's where we get the 0. And then that's where if you add this M1 V1 to itself, that's where you get our first term there. So hopefully seeing in detail where this easy part comes from, the other part becomes a little more understandable, right? So when we look there at our end, we have to look at, we're now shifting to our red circle here, right? I'm going to take off these underlines because they're getting in the way. Right, now we want to focus on these two terms, all right? And that will occur from looking at these two masses, right? So we're just going to start with V1F. You'll notice it's moving at its M1. The mass remains unchanged, right? So we still have that M1 term. And you'll notice it has a new, fancy new speed. Now you'll notice I did not use this incorrectly. Here on the graph it has a velocity, but in the equation here it's a speed. And I want to review that we've seen this. We want to remember that the x component. Remember that for a velocity vector, I'm going to write it down here at the bottom. We've got some space. Pick another color. I like purple. Purple doesn't, for being my favorite color, I don't usually use it that often, probably because it is my favorite color. So any velocity vector, right, will be equal to Vx I hat plus Vy j hat, right? So recall chapter 3 for vectors. So we have a vector here, but we're looking at the x component. And you'll recall that the x component, right, if we just want to look at this, Vx is equal to the speed, right, V final, times the cosine of theta 1. All right? And if we look at that, and we know we have the and we get the cosine theta part from analyzing the triangle, right? If you make a right triangle here, down to the vector, now with theta 1, you have this, let me delete this part of the circled part. So we already looked at 1, so we can delete that. And then now we're concentrating on the second part. So you can see with the right triangle that I made, the x component, cosine of theta, is the adjacent over the hypotenuse, right? With the hypotenuse being the full vector. So that gives you, very naturally gives you that x component. So keep in mind that, and when you do that, when you break the into the components, the p component is just m times v. So you multiply by, so px will be equal to m vx, and you get the first term. All right, and you do the same thing for the second term. All right, it's the same process. You look at 2, you make a right triangle. I'll make that for you. Right, you just drop down to make a right triangle here. And you'll notice again with this theta angle, the adjacent over hypotenuse is the cosine of theta 2, and you can use that to decompose and get your second component in x. Okay? Questions so far? We're just talking about along the x component. Good? All right. So you'll notice for the y direction here in this particular problem, they've sort of stated that well, they didn't have to state anything, right? The initial, there's definitely y direction in the final, but you'll notice in the initial picture, there's no y direction, right? So we can just say the momentum in the y direction initially is 0. All right, and that's because if you look here, this is stationary, so it's 0, 0, and this is only moving in the x direction, so there's no y component. So we can see there that our initial momentum is 0, and we just do the same thing we did before, although you'll notice that both of these were in the positive direction, right? These are both moving in positive x, but you'll notice that one is moving in the negative y direction, so you get a negative sign here, and then you just get that x component, and then you'll notice it's moving in the positive y component for the second one, and that's where we get this positive term. Again, the sine thetas just come from the vector decomposition, right? Or that's just components of the velocity vector. And then our final equation, because we were looking at an elastic collision, is that the energy is conserved, right? And again, there's only one term on the left-hand side because the initial speed of m2 is 0. It's stationary, so it has 0 kinetic energy. And you can just, and all the energies are kinetic here, so you can just apply them. All right. So again, this was a good example of how to construct the problem, right? Any problem you have in 2 dimensions will almost certainly be constructed this way. If it's an inelastic collision, you have to cross out the energy for inelastic collisions. So I'm gonna take that out actually, because I said it there, but I'm actually going to type it. So for inelastic collisions, actually I'm going to add completely so that we're, for completely inelastic collisions, cross out energy. All right, and I'm going to do it here with the pen to make it all sorts of dramatic when you're watching later. So only for an elastic collision, you can use the energy equation. But if it's inelastic, you got to cross that out. All right?
Okay.
So let's look here. These 3 equations have a for a stationary target, all right, have 7 unknowns. Let's count. Let's go back to a clean slide and count them. We have theta 1, theta 2. Let's count what we have. We've got theta 1, theta 2, right? We've got V1 initial, V1 final, V2 final. So that's 1, 2, 3, 4, 5, and then M1 and M2. Wow. So we have 7 possible unknowns here. So, but we only have 3 equations, right? So if we have 7 unknowns and 3 equations, we must know 4 of them in order to get a solution. All right? So you always want to work out how you can have 4. And in fact, for a non-stationary target, there are 8 of them. So you must know 5. You need to know 5 equations or 5 quantities to solve for them. All right? So keep that in mind. Your goal will be to interpret your problem to sort of sift out your knowns. Because as I will give you the grand hint that when we pose a problem in the book, the answer will almost never be there's not enough information to solve. I don't think I've assigned a problem where that's the answer. I've certainly never given it on a test. And I think there's one or two in the book, like if you look really hard, you can find, oh, there's not enough information to solve. But I don't want to send you all down that rabbit hole. I'd rather you know that you can solve it, and if you can't find the information, you need to work harder. I think that's, geez, why is this thing so loud all of a sudden? I think that's enough for the class, right? That's what we want to, I don't want you second guessing whether the solution exists. You can have confidence that there's enough information. Now, whether you found it or not, that's an issue. So let's look at a checkpoint. Checkpoints are always fun, and we'll have an example that we'll work through, which should get us a good amount of the way to where we want to get to. So in figure 921, suppose that the projectile has an initial momentum of 6 kilograms meters per second and a final x momentum of 4 kilograms meter per second and a final y component of -3 kilograms meters per second. For the target, what then are the final x component and the final y component of the momentum? Wow. So if we look here, we can decompose from our previous equation. We have, well, first of all, why don't you work on it a little bit? But keep in mind that this is a general problem at the level that we first wrote it. So you have px initial equals px final, and you have py initial equals py final. So you won't have to break things down into components, but this will be how you solve it. So see if you can, knowing this, see if you can break down everything and rewrite the I'm going to redraw the figure up here in purple. So you have your initial system, where this is M1, V1. Remember, M2 is stationary. So this is the initial system. And then you have, hold on, let me finish drawing this. M1, V1, M2, V2 final. Yeah, what was your question? I think it was Alvin asked a question. Finish drawing here. So that's the figure, right? Where you have, this is your initial. Did you have a question? Alvin? I can't hear you if you're talking. All right. Well, you might want to try typing it up because I'm not hearing you if you're talking, unless you're typing and you're going. But I'll just keep talking until you ask. So give it a shot. See what you get. And yeah, I'll give you a minute to do that one. Okay. Anyone want to give a shot as to what the answers are? Okay, that's telling me my lack of beeps and boops are telling me that it's just a little too that this one might be a little more challenging. That's okay. Um, so let's take a look at it from the perspective here of our picture. All right. So let's look at it just like we did the last one. So we're going to start with in X. All right. We have P1X initial, right, equals P1X final plus P2X final. All right. And we can look from here and see that this implies that P1X is 6. And that's going to equal 4 plus P2X final. All right. So we can see here that this implies that P2X final equals 2 kilogram meters per second. Okay. So I think the hard part here, since I didn't get my boops and beeps, as you can see, the math is very easy, right? And I've sort of told you that, and I'll continue to tell you that, and that's no big deal. But what's important here, and I think this problem actually, considering we're just learning about collisions, is actually a little challenging to translate. But once you translate it, it's very easy. And I think the reason why it's hard to translate is because the math is so easy, right? Because you're thinking, well, we just talked about going into components, and usually when I ask you about speeds, that will be true. But if you have momentums, it becomes very, very trivial. It's very simple. So now that you see how A is done, does anyone want to give part B a shot? I want to see if having seen that, if we get a little bit more of a better response, if we can do in Y. Setting up the problem the same way. All right. See if you can after seeing it in X, if you can see it in Y. No, we're a little bit all over the place. So for A, we definitely got 2, right? And for, I don't know where 9 came from, Martin, but if we look here, right, we have P2Y initial equals P2Y final, or P1Y. Actually, we have both of these. Sorry. I want to delete this because there was definitely a second term here, but it was 0. And we know the same thing will equal 0 here, but it's just 0 plus 0. So I'm going to delete this. Why am I deleting this? I'm deleting this because there was a P2. We know that P2 is stationary, right? So I'm going to do it the same. So since we know P21 is stationary, we'll do P1y again. I like that better. Equals P1y final plus P2 y final. All right, but we notice that our initial motion is only on the x direction, so this will go to 0, and we can say that this implies that 0, right, equals 3 plus, or minus 3 rather, plus P2y, and then we can see that P2y must equal 3 kilograms. Oh, I'm just going to multiply the meter there. Okay, does that make sense? I'm hoping that the process makes sense, and I realize, I very much do realize we've got to practice and work on it. And I already looked up the homework. The homework has been assigned for the rest of the semester. So I don't know if it's dropped yet, but you should be working on the homework. Should be available. Also, I think I recommended this to the Physics 2 class. You'll notice I only assigned 2-star problems, but the 1-star problems are very, very easy. And if you want practice or you feel like you're confused, open up some 1-star problems and try doing them because they're just simple, right? There's not a lot involved with them. You just sort of plug things in and get comfortable. And I always, if we were in class, I would be telling you to work on those on your own. So to consider those sort of, you can sort of consider this. All 1-star problems are assigned. I'm just not grading them. So you can do as many or as few as are useful to you. That's how you should think of homework. Because a lot of students think I assign a little bit because my assignments are a little shorter than some of my colleagues, but they're all harder problems. I don't assign any of those level 1s. Sometimes if the application is really good, I will assign one, but that's if it provides really interesting context outside of class. And that happens a lot more in Physics 2 than in Physics 1. So I think we're good here. Let's go to our example, our big example, and I want you to try and set up this problem, and I want to go over it. Okay? I want to get a feeling for this problem, and to for you guys to solve it. So try it for about 5 minutes on your own, and I want you. So what we'll do is we'll take. I was going to say we'll take a shorter break, but I'd like you to work on it for about 5 minutes, and then at 2 we'll take a 10-ish, a little less than 10-minute break. We'll take a shorter break today because we got started a little late, and we'll go over this problem. Okay. But I want you to try it. I'll read it first. After completely inelastic collision, 2 objects of the same mass and same initial speed move away together at half their initial speed. And it wants you to find the angle between the initial velocities of the object. So you want to look at that and see if you can. First, there's 3 steps to this. First, the first and the hardest step is, can you draw it? The next is, can you then interpret the math? Interpret the math. All right, and then can you solve for it, right? So that will be what you need to do. So I will be on the horn, if you will, here for the next 3 or 4 minutes, and then I'll take my break. And again, it won't be a very long break because it was a little slow start this morning. And then we'll go over this problem. This is a good problem, and you'll notice it's 2 stars. Again, don't freak out if you're struggling with it. I really want to encourage you to try and struggle with it a little bit, get frustrated, and we'll go over it because if the more frustrated you get working on it, the more it'll sink in when we see why you should, when you see the solution to your frustration. Whereas if I just do it, you'll get something, but not nearly as much. So, but you can ask me questions and stuff like that until I put the away sign up. Oh, we've got some disagreement, but good. We're still going to go over it because there's 15 people in here. But I'll tell you this: one of those answers is right, and one of them is less right. So. All right. I'll come back. Well, we will all will be revealed after we come back from break. So I'll be back in around 5, or, I want to get started around 8 after, so I won't be too long. I'm just going to get a quick drink of water. So let's take a brief pause, and I'll be back shortly. Back. All right. So let's go through this. Well, you know, I have to have some fun too, right? Um, okay. So I think the hardest part is drawing this, and I want to point out, um, that a lot of it's arbitrary. Oh, that's right. There we go. So if you look, the axes are arbitrary, right? What you really have, and I want to draw it up here, is you know you have these two things moving towards some point, right? It doesn't matter what that point is, and you know that there's some angle between them. And this is what it wants you to find. I'm going to call that psi because I've already taken theta and phi down here. Now, what you can do is you know that once they get to this point, they're going to move together as one blob. So you put your axes. The idea is you assign your axes and say that the x-axis is going to be, you just flat out choose it to be this axis in which the combined object moves. All right, so the combined object's going to move on that purple axis. You just make an axis there, and you have your y-axis. You can see that dotted. And now that you have an axis, you can say, okay, well, with respect to the x-axis, one of the top mass will make an angle phi, and with respect to the bottom, the other mass will make an angle theta. This is the most general way to look at this problem without assuming anything. The only thing they've looked at here, because I would call this M1 and M2, or hold on, I've got the straight line up there. So I'd call this M2. And then we can delete these when we recognize that M1 equals M2 equals M. Then we can take away the subscripts, right? And now we have our drawing, although we should really have here V1 and V2 as well. But you'll notice it says the two objects of the same mass and the same initial speed. So we know that the speed, we can take away these subscripts now. Okay. So one thing we can notice is that our final this is an inelastic collision, so we know that our P, our final momentum, will be the sum of the masses, so 2m, in the y direction times the speed in the y direction. Now this is the beauty of choosing your axes. We've chosen our axes so that we're only moving in the x direction. Therefore, we can say right away that this is 0. All right? So we pick our axes so that it gives us something like this, and we can right away go 0 equals P1 initial, right? In the y direction, plus P2 initial in the y direction. And we can look at that, and if we look at our first, we can go down and look at our bottom mass here, and I'm picking that one first because I know it's moving in the positive y direction, whereas our top one is moving in the minus y direction, and I just want to keep everything, you know, positive. So we can see that we have v sine phi, or m phi sine phi, and, or sorry, that is incorrect. We have mv sine theta minus mv sine phi, and that's going to be equal to 0, right? So we can see here then that mv sine theta equals mv sine phi. And this implies that theta equals phi, right? So that's one part of it. I need to move so that it becomes unselected. So that's our first step, right? So does everyone see that one? Okay, so hopefully that makes sense. And we can now go into the X region, right, where we have, let's see, we have MV cosine theta plus, and I can write it as cosine theta because we just proved that phi was equal to theta, right? So that makes life easy. That's on one end, and that's going to equal 2m times the final velocity of the system, right? So we can simplify this side. This will just be equal to 2 mv cosine theta on one side. And recall that they move together at half their initial speed. So we know that big V equals little v over 2, right? So we can write this here as 2 mv cosine theta. That's going to be equal to 2m v over 2. We get that there. And we can see the mv's cancel now. And we get cosine theta is equal to 1/2. All right, so if you solve for theta equals 60 degrees, but before those people who had 60 degrees get excited, it asks for the angle between them, right? So it wants theta plus phi. We'll call psi is equal to theta plus phi, which is equal to 2 theta, which will equal 120 degrees. Okay? So the 120 degree people are correct. And hopefully if you didn't see it, you see why. If you got lost somewhere and have a question, think about it. I'll give you a minute or two to sort of marinate and see if you have any questions about this. And then at about 2:20, we'll move on. 2:21, we'll move on. Okay? Uh-oh. This is not good. Oh, wait a minute. What is that? Where did you come from? Uh-oh. That's never a good feeling when you see something, a part missing to furniture, and you don't know which part it is. That's not good at all. Where did it come from the case? Did you? All right. So if you have questions, you can feel free to ask as we go along, but hopefully that makes sense, and you can stop and look there a little later. We are done with Chapter 9, so that's good. And we will now move into Chapter 10. So now we're going to go into rotation. All right. And basically, this is sort of a half and half chapter. We're going to be learning some new concepts and extending them, but chapter 9 sort of takes us through our basic concepts of Physics 1. Our new concepts, we are going to be learning new concepts, and they will be physically different, but they will be developed using the same logic as stuff through chapter 9. So they will be equivalent, if you will, or analogous. So a lot of the math is the same. So I won't spend a terrible amount of time on it. I'll point stuff out, but it's exactly the same as the linear stuff. And I'll sort of talk about, like I said, I'll talk about it, but you know, going in depth, I don't think should be as necessary here because again, none of it's new. I mean, we should be a little used to it by now, hopefully. So let's talk about what looking at rotation allows us to do. So up to this point, we've been learning about translations, right? And when we make a translation, let's take a look at a rectangle, right? I'll color it in. So if we take a look at this rectangle, if we're looking at this rectangle translating, right, that just means if it were moving across the screen, you know, towards the Wiley words, what we would do is we would treat it as a point, and all the forces and things would be acting at this point, right? We could have forces acting in any which way, and everything would be at this point. What rotations allow us to do is look at forces and behavior where we can look at the entire object as a whole. And let me show you what I mean by that. Okay, so what we do is we're going to change colors. I'm going to go with red. And we're going to put in a pivot point here, right? So this will be fixed about that red dot pivot point. And now you'll notice if a force acts here or acts here, this will cause a different type of motion, right? One of these will cause it to rotate clockwise, one will cause it to rotate counterclockwise, and you'll notice you can no longer assume that those forces act equivalently at a point. You can't reduce this object to a point. So adding rotations to our repertoire allow us to look at more complicated systems, and basically we're going to learn about, we're sort of going to, what chapter 10, one of the reasons it's so long is because we sort of redo everything we did for the first 9 chapters, but now with rotation instead of translation, and we just sort of plow right through it. We sort of get through the whole thing. So the next 3 chapters will allow us to sort of look at, consider systems of what we'll call rigid bodies. All right. So the rigid bodies, this means it's uncompressible. So think of like a pen that you can't squeeze or something like this. Like pretend it's steel or a bolt. Everything moves together and everything stays connected and locked together. And if you put a fixed axis around it, it all rotates together. So that's what we mean by a rigid body. All right. We don't mean like a slinky or something that can move, that's non-rigid, or a fluid basically, or a gas. So we'll find new quantities like torque and rotational inertia, but we're going to find that torque is similar but different from force, and we're going to find rotational inertia is similar but different from mass. All right, so there will be new techniques here. There are definitely new techniques to solve, or develop these quantities for rigid bodies, but they are analogous. All right, some of them are straightforward, and we'll see those quantities first. But then when we talk about torque and inertia, there's going to be work to get those, but they are what they are. So you'll notice that when we talk about rotation, our axis is going to be important because we'll have a rotation point or a pivot point. So we look at rotation around a fixed axis. So now our axis is going to matter a little bit. And that's because we need to have a pivot point or an angle with respect to something to define the rotation. So that makes it a little bit more complicated than we were used to before. So things we will not consider is the sun, which is complicated, right? So the sun has layers of gas that rotate separately, and they rotate differently. And gas is not a rigid body. But so this won't be. This would be your chapters on gas. So if we get to thermo, you'd cover this there. And this is chapter 11. So rolling bowling ball is not what we're going to cover here, because chapter 11 is rotation, which we'll learn now, plus translation. And that gives you rolling. Okay? So let's sort of get through it. Now, the fixed axis we'll use is called the axis of rotation. And I want to show you, you have an egg here, and you can we'll look at the individual parts. But then I want to do sort of a very simple example to show you exactly how this changes. Now, we have the fixed axis on the rigid body called our axis of rotation. And the reference line, which you'll notice is here, it just sort of says that's what we call 0, right? And any angular displacement, it's going to be a new quantity, from that reference line will be equal to some angle. All right? So we have the reference line sort of screwed into the body that's rotating, and as it rotates, right, the reference line changes and you get an angular displacement. All right? Now, again, we put the reference line at a position of 0, initial position of 0 angular reference. And as you notice, this body is rotating about this axis. Okay, so that's why, so you're not looking at it going up, you're looking at it going in. And your reference line is there, and you have this theta value. This isn't the best picture of this, honestly, to tell you the truth. But it is what it is. You have your arc. So, I think when they do this, rotation axis is out towards you. But we already have a rotation axis. Oh, I see. Okay. I'm getting ahead of myself. So this reference line, so this rotation so there are two different rotation axes. I messed up. Sorry. So here we have the rotation axis along this line, and you can see that'll give us this classic theta. I was going to say this picture was too bad to be correct. I thought these were A and B to make the point. So this is rotated, and this reference line will just go around in this circle, okay, with this z-axis being the rotation. They're doing something I never recommend you do, which is you'll notice they have the XY rotation here, and then they're picking it up and rotating it. That will lead you, if you're very careful and correct, you can do it just fine. And that's essentially what they've done here, right? They've picked this egg up in A, like so. So if they've said that, and they've said, okay, now we're going to look at this rotation rate, and we're going to move that z-axis into and out of the board, and that's what they're doing. So the rotation axis, the equivalent axis here, if you look, so notice this is the circle I'm making is in the XY plane, right? My terrible circle. And you'll notice this circle here, the dotted circle, is also in the XY plane. So they just picked up this egg and rotated it, and that's what they're doing. And again, I want to show you, let's just look at a simple rod, right? I mean, we want to, this is true for everything in general, but you're going to see that if you have 3 different rotation axes, those will be 3 very different, those will look different, right? So imagine, let's look at my pen. Imagine you put, I'm actually going to stop sharing this for a minute because I want this to be in the lecture. And the video won't be if it's not. So let's, let me go to my slides. I'm going to stop sharing for just a minute. So my video hopefully should be what all of you are seeing. Now, so imagine we have a rod, like so, and if I put my finger as the axis of rotation, It'll start rotating like that now, right? Just dropping everything. Now, if my axis of rotation is in the middle, it'll start spinning like this. And if my axis of rotation is here, it'll start spinning around that axis like so. Okay? So I hope you see that there's different rotations depending on the position of your axis. So having a fixed rotation axis is critical for solving rotation problems. You need to know where that is. All right? Because the motion or the rotation changes depending on the axis location. All right. Let's get back to slide sharing. Share now. All right. So hopefully we cleared up any confusion on this one, and now let's get to the quantities. So the angular position, all right, let's keep it super simple. Angular position is given in theta, and it's just like you think it is. If we know right, so if we have a coordinate system, so when we look here, we'll have some, so basically you'll have some arc S, some radius R, and then you'll have an angular displacement of theta. All right? So you'll notice that this all sort of makes sense. Your arc length S is equal to theta R. And of course, if you make one complete revolution around the circle from the reference point back to the reference point, you have theta equals 2 pi, right? For one revolution, for a single rev. All right, so in that case, S rev will be equal to 2 pi r, which you'll notice is your circumference. So you'll notice the arc length of a revolution is the circumference, right? And will be equal to 2 pi times r. And that again is just recognizing that going around once is theta equals to 360. But any intermediate arc length can be found in terms of the radius and the angle. And now if we look at, what we'll look at on this graph is we'll call this our theta initial, and this would be theta final. So what this will allow us to do is, now that we have these angles, is we can define the angular displacement delta theta is equal to, remember, it's always final minus initial. And what we can also see from here is that much like we had translation as a function of time, we will see that here that we'll actually can have theta as a function of time as well. All right, and we're going to start to look at the dynamics of rotation just like we did for the dynamics of translation. And just like translation, once we have the position vector, or the position as a function of time, we can figure out everything by taking derivatives. And the same thing will be true with theta. We just have to learn about, now that we have angular displacement, we'll have to learn, I bet you can guess, about angular velocity and angular acceleration. All right? So, clocks are negative. So what does that mean? So we have to, so much like we had with displacement, we had to have backwards and forwards motion, right? We had to tell the difference between negative x and positive x. So the same thing is true for for angular displacements, but we use our standard right-handed coordinate system convention, right? So if we make that line there and this line here, so if we have, I'm going to make a circle. I'm going to move the circle. So basically, if we change colors here, if we're rotating counterclockwise, counterclockwise is positive. And if we go clockwise, is negative. All right. So you want to keep that in mind as you're going through your angular displacements, that you do have positive and negative rotation, just like we have before, and we aren't changing conventions or anything. It's all the same like you remember it. Now let's do a simple little check here, a little checkpoint. A disk can rotate about its central axis like a merry-go-round, right, or a carousel. Which of the following pairs of values, all right, for its initial and final positions respectively, so that means this is initial and this is final, will give a negative angular displacement? All right. So I'll do A with you, and you can hopefully do the rest. So we have final. So we want to know, is delta theta negative? And we want to remember that delta theta is equal to theta final minus theta initial. And for A, theta final is equal to 5, and theta initial is equal to minus 3. So we have here delta theta is equal to 5. Nope, yeah. 5 minus negative 3, and that is going to equal 8. So A is no, right? A is not negative, it's positive. So work through the rest of them and see which ones you can, which one of these are going to be negative. Good, good. B and C are going to be negative, right? A, if you'll notice, is in, you've got your, oh, there's only B and C. I thought there was a D. So you'll notice B and C are negative, and A was not. So good. All right. Just go through the procedure and add those numbers, and I'll show you one of them. So we'll pick C, right? In case you're not seeing it. So for C, again, delta theta equals theta final. So we're going to call this C minus theta initial. So theta final is going to be minus 3 radians minus 7, right? That's the initial. And that's going to be equal to minus 10. Okay? And so we have minus, so it's yes. And I'll leave B as an exercise to the student. Okay. So now that we talk about angular position, it's pretty simple and straightforward to look at angular, the average angular velocity as just delta theta over delta t, which you'll notice is pretty analogous to velocity, right? Linear velocity, which is delta x over delta t. And just like we could before, this is the definition. If we take the limit as delta t goes to 0, we get a derivative, okay? So if the body is rigid, these equations will hold for all points on the body. This is important. It means that different parts of an object can't rotate at different speeds. all right? And so the magnitude of the angular velocity will be the angular speed. Now, looking at these as vectors gets a little complicated, all right? So we're going to notice that we're going to have to use our right-hand rule, and for hopefully for reasons that become obvious as we go, but it's not going to be obvious right now. But basically, the angular velocity is orientated perpendicular to the plane of rotation, all right? And if you use your hands to curl down, to rotate with your body, right, like this, and you close it and you stick your thumb out, that will give you the direction of your angular velocity vector. But rotation stuff is very counterintuitive, all right? And if I could share YouTube videos with you, which I can't, there are several things that make this look easy. I'll try to find a link to a few of them and put them in on Blackboard or something so that you can watch them or send them, or when we talk about torque, I'll just provide them and you can watch them as part of the lecture. So yeah. But like I said, the direction, not very intuitive here. All right, notice it's perpendicular to the motion you would see with your eyes. Now, you can see sort of a similar angular velocity velocity calculation here, right? That we did for our rotating body. You'll notice you have theta 1, theta 2. This gives you a delta theta, and you have theta 1 at t1, theta 2 at t2. You have everything you need for an average angular velocity calculation. And of course, the angular acceleration, you'll notice we're sort of just flying through these. It's, again, we had with linear acceleration, right? We had A equals delta V over delta T. So if we have, so it makes sense that alpha here, which is the angular acceleration, will be equal to delta omega, which is our angular velocity, right, over delta T, which is what you have right here. Okay, and again, it's set up like if you take that limit as t goes to 0, you will get a differential, which I believe they do on the same slide here. And again, this point is important, all right? The bullet point here. All right? Because this tells you that everything moves and rotates together. Again, you can think of this like, I know we don't use optical discs anymore, but if any of you have ever played a Blu-ray or a DVD or a CD, heaven forbid, you'll notice that the disc spins, right? So that a CD is or optical discs are great examples of rigid bodies because they have art on them. So because they all rotate the same way, the art stays the same. If different parts of the disc rotated at different speeds, it would all become a jumble, right? So these conditions are required of rigidness, have to be maintained in order for these equations to apply. So with the right-hand rule, you can determine the direction of angular velocity and acceleration, and they can be written as vectors. If the body rotates around the vector, then the vector points along the axis of rotation. So you'll notice here that angular displacements are not vectors because the order of rotation actually does matter for rotations around different axes. So this is a little weird, and we're actually technically getting into the realm of pseudo-vectors, but you need some really complicated math to look at one-forms and pseudo-vectors and vectors. So because they behave almost completely like vectors, we get away with calling them vectors, but the math you would need would be very advanced, like tensor calculus, which is a specialized math that most math majors don't even take. So you would need to take a geometry class, a tensor class to get into this type of math. To understand sort of exactly the difference between these things, you need to get into some really high-level stuff that engineers never see, to be quite frank. Most physicists never see it. I've seen a little bit of it, but most experimental, you'd have to be a theoretical physicist like me to see it. Well, actually, all of us here are theoretical, but like it's stuff Professor Kalfin and Professor Senkov have come across we're a little more math heavy. Professor Sheffield and Professor Tan do a lot of practical astronomy, so they know a little. They've got a handle on a little bit of it. Professor Tan likes numbers though, so he might have seen a lot of it. If you ever want to have an interesting conversation with someone about large numbers, Professor Tan knows quite a bit about weird representations of extremely large numbers. He's a fun guy to talk to about that. But yeah, to make it simple, we're just going to call these vectors, which behave like vectors. And by these I mean the angular velocity and the angular acceleration. But angular displacement will not be a vector. And essentially, which hopefully you do take a vector, a linear algebra class at some point, they don't transform like vectors. Vectors have to transform like vectors, and angular displacements do not. All right, they are not invariant under rotation. Okay, so now that was basically chapter 1, right, or chapter 2. Now we want to go through chapter 3 with rotation, or chapter 3 and 4. So you'll notice here we have these, if we assume a constant angular acceleration, you'll notice that we can actually just change our linear quantities to angular quantities. And what I mean by that is, let's take a look over here. So you'll recall in chapter 2, right? If A was constant, we were able to develop equations for V and X. So now if we assume that alpha is constant, right, all we have to do is replace A with alpha, V with omega, and X with theta, and you'll notice that 211 becomes 1012, almost perfectly. Well, actually perfectly, right? You can just replace each one. And you'll notice you go down the list, you can replace each one because the calculus again remains the same, right? If you have A as constant and integrate it up, it's the same as having alpha constant and integrating it up. It's just now you have omegas and thetas instead of x's and v's. All right? So where this stuff becomes more important is in the checkpoints. And you'll notice these checkpoints look a bit like chapter 2. So we have 4 situations. A rotating body has an angular position, theta t. It's given by these 4 trajectories. To which situations do the equations of table 10.1 that we just saw apply? So the question is, when do these equations apply? That's the big question. What must be true about the angular acceleration for those equations we just saw in the last slide to be true? I'm leaving this one up to you guys. I'm going to keep moving my desk, which I'm not thrilled with, but so I'm going to fix my desk while you guys answer the question. I can bolt them together, but that would be too obvious of a solution, and we can't have obvious solutions now, can we? So what's got to be true? I'll give you a hint. It's staring you right in front of the face. Well, that's how you find the double. You can always find a double derivative. What has to be true about the double derivative or the second derivative? What condition must be true for these equations to apply? Right? So when can you use these equations? What has to be true about the angular acceleration? It has to be constant. Good. So when the angular acceleration is constant, you can apply the table. So now we know that alpha equals d omega dt. equals the second derivative, which was very good. So how do you prove, so now how do you investigate these to find out which ones are constant? Or do that. So let's take a look at A. All right. So the first derivative, so for A, d theta dt is going to equal 3, and d2 d theta is going to equal 0. 0 last time I checked, so here alpha equals 0. And last time I checked, 0 is a constant. So A, we can apply the equations. All right, C and, well, let's look at C and D. So C, I'm going to rewrite this as theta equals 2 t to the minus 2 minus 4t to the minus 1. Because I don't like quotient rules, and I'm lazy. It really doesn't come, it really just is that. So d theta dt is going to equal to minus 4 t to the minus 3. And this is going to then be plus plus 4 t to the minus 2. And then if we look, this isn't looking good for constant acceleration. If we look at the second derivative, right? That's going to equal 12 t to the minus 4 minus 8 t to the minus 3. So as we can see, that's not going to, if you want to write this in a equals 12 over t to the fourth minus 8 over t cubed, right? So that's not going to be constant. So D is or C is definitely no. 3, it's easy to see, right? With that second derivative, you'll still have a t term, so you can cross that out. But you have a t squared term here, and if you take the second derivative, it will just be 10, I believe. So that will work out. Now, I just want to be sure we have this right here. Okay. So what time is it? Oh, we've got 20 minutes. We can move on. Any questions on this one? Always good to stop and ask questions. Okay. Just chime in. And up to 2D power, right? So to the so just like we've always had, Artin. In order, just like we had in chapter 2, if the power of t is any more than 2, the higher order derivative will always be make there be a factor of t in the equation. So yeah, so basically you need to have t to the second power, t to the first power, or 0, right? Those are your things, your restrictions. Any other power value will not lead to constant angular acceleration or constant acceleration. Yeah, because the second derivative is constant. And in order for those rules to apply, in order for kinematic equations to be used, that acceleration has to be constant, which means that the position cannot be of a power greater than 2. Okay? Yeah, that's just the calculus there. All right. So now we want to relate our linear quantities, which we already saw how to do with angular position a little bit, to our angular quantities. All right? Now, when we look here, we have linear and angular variables are related by the radius, which is usually fixed, all right? Which is the perpendicular distance from the rotational axis. So let's take a look at this. Let's take a quick look at a circle here, and nope, that's not a circle. All right, so there's a nice circle, and let's give it a radius. So you'll notice as you rotate around the circle, that could have been better, but the radius is always fixed, right? So we have some given arc length of the circle. Nope, this is wrong. That's got to be deleted. We have some given arc length, right? S is going to be equal to theta times r. And remember, we already saw that for one revolution, theta is equal to 2 pi, and you get the circumference. But now we can look at this and we can use our definitions, right? We can take the derivative of both sides, d dt of s equals d dt of theta r, right? But r is constant. That's the beauty of r. Is the radius of a circle, r has to remain fixed. And you'll notice that r is that the rotational axis is coming into and out of the board, and so you'll notice that r is perpendicular to that axis, right? So if you look at my circle and you have your thumb pointing straight at you, r will be at that fixed perpendicular distance. This is interesting because this is fundamental for looking at fields, E-field values along axes of shapes for the electric and magnetic field. So you will be using stuff like this a lot in physics too. But let's look and develop this equation here. We can see that this implies that ds dt equals d theta dt times r, right? And recall that ds dt is simply the velocity, and d theta dt, as we just saw, is omega, and r is r. And so that's how we get this equation here. And we can do the same thing to get that the acceleration is equal to alpha r. Now, you may be wondering, well, wait a minute. I know that when I move in a circle, a is equal to v squared over r. And this is very different. These are not the same. This will be the radial acceleration, and this will be known as the tangential acceleration. And in fact, what we'll see is that the total acceleration, the magnitude of the acceleration, will be equal to the tangential component squared plus the radial component squared. Okay? So we will see that sort of complication develop as we go forward. But we just want to look at this here, and we'll get to this this acceleration part formally in a little bit. Actually, I think it's the very next slide. So we'll see that written more cleanly. But let's clear this first and take a look at the period. So we know that the period, right, is the time it takes to make one revolution. So if we look at our, if we know that x, hold on, x equals v times t, right? So we can replace this with delta theta equals omega t. And if we make delta theta equal to 2 pi, that will be equal to omega times the period, right? That's the time to make one revolution. And then we can solve for the period, and we get is equal to 2 pi over omega. All right? So you'll notice when we did this here, we had it is equal to like 2 pi over, or 2 pi r over t or something like that. There was some expression for it in chapter 4. I'd have to derive it again. I don't remember it. So that should make sense. And then now we have sort of the more formal version of the tangential acceleration, right, which we derived in the last slide. At equals alpha r from just taking that derivative. But we also have a very different radial acceleration, all right? And you'll notice that the radial acceleration can be written in terms of omega as omega squared over r. So let's try and prove that by substituting stuff in, okay? So the claim here, so let's look at A. Radial equals v squared over r, right? And we know that v equals omega squared r squared over r equals omega squared times r. So we can see where this comes from. All right? But you can see here for something rotating, right, in sort of non-uniform circular motion, you could say, you have a tangential component to your acceleration. That's so AT points tangentially along the curve, like so, and it points in the same direction as the velocity vector, all right, which is always tangent to the circle. And then you have the radial acceleration. And you'll notice that you can combine these and add these vectors to get a complete acceleration vector, okay? Pretty neat. Well, I think it's neat. So any questions about that? I think that's a good place in the middle. If we have a checkpoint, yeah, we want to stop. So I'll let you read this, and you can try to come with it next time, the answers. But we will this problem next time, and we will next time being tomorrow, and we should hopefully get pretty far into. We actually got a lot farther than I thought we were going to get. I'd initially planned to end a few slides earlier, so we're making pretty good progress. Like I said, so I'm going to stop recording now. This is where we'll pick up tomorrow.